Welcome, pre-calc honors students. Here we are with the other trigonometric functions, and we're going to try and learn how to sketch these as well. So let's look at the definition of the other four trigonometric functions. They start off the same way with a point on a circle, x squared plus y squared equals r squared, and theta is the angle in standard position. But now we take and do the tangent as y over x, the cotangent is x over y, the secant is r over x, and the cosecant is r over y. One thing I want to point out here too is that we have some restrictions that we didn't have before. Because before we were always dividing by r, and r was always a distance from the origin, we never had to worry about this undefined possibility. So there are some times when these other four trig functions are undefined, and we'll see those in the graph. Now you should know these identities. These are called the quotient identities. That is, the tangent of theta is sine over cosine, the cotangent is cosine over sine. These are your reciprocal identities. The secant is 1 over the cosine, the cosecant is 1 over the sine. Down here is just all the different variations on the tangent and cotangent reciprocal ideas. You can do that with the secant and the cosecant as well. Here's example 1. Find the value of each expression of 4 significant digits. It's good to have your calculator out here so you're familiar with where to find these things. Now the fortunate thing is that TI-89 does actually have these in its catalog, cotangent, SEC written exactly like that. So even though you only have sine, cosine, and tangent in a middle row there on your TI-89, you can get these other ones there as well. Did you try them? Here are the answers. Some calculators don't even have these, so you have to write as 1 over tangent. Now here's example 2. If theta is in a second quadrant, angle and tangent theta equals negative 3/4, find the values of the other 5 trig functions. Okay, so let's try this. Okay, so we've got the tangent of theta equals negative 3/4, and we're in the second quadrant. So let's put that idea together first. Tangent of theta is negative 3/4. Well, tangent is y over x. So you see how this leads to one equation and two unknowns. Now, we could pick any point on the terminal side of an angle theta. We want to be in this quadrant. So do we want the y's to be negative and the x's to be positive? Or do we want the y's to be positive and the x's to be negative? I think the latter here, because we want to be in quadrant 2, where the x's are negative and the y's are positive. So I'm going to look at this as the point negative 4, 3. And conveniently, we can get r with the square root of x squared plus y squared. And I think you can see here that we've got a nice Pythagorean triple there. Negative 4 squared plus 3 squared. So you get 5. So that's 5. So there's our x, y, and r. So we can use x equals negative 4, y equals 3, and r equals 5. And from this we can get all the trig functions. Sine, cosine, tangent. I usually list them in this order to remind you that the tangent is sine over cosine. Cosecant, secant, and cotangent line up this way because these are the reciprocal identities, and they're just 1 over the answers we'll get here. So if the tangent was negative 3/4, and our r is 5, that goes in the bottom of the sine and cosine. The sine is the y coordinate, so that's 3/5. The cosine, the x coordinate, negative 4/5. And then we can flip all these. So the cosecant is 5/3. The secant is negative 5/4. The cotangent is negative 4/3. There we go. Now we're ready to look at the tangent graph. And for this, let's take a look at something that I've generated on GeoGebra. This is a similar structure to what we used before to generate the sine graphs. But in this case, we're not looking at the height, because the sine is how high you are on the unit circle. No, here on this unit circle, I've drawn a tangent line from the point of tangent, see here. And the actual tangent ends up being this length from the point of tangent to where the tangent crosses the x-axis, which we'll see later on as the secant line. And as you rotate this around, you can see how the tangent changes drastically. It's not just one coordinate anymore. Okay? So see how it's this length along here. And you can also see some spots where it's undefined. First of all, if we come all the way down to 0, we can see that that little tangent segment shrinks to 0. So the tangent of 0 is 0, much like the sine of 0 is 0. But now as we stretch it here, here's our tangent of 45 degrees roughly. Now we're getting a tangent of about 1. And now as we head up to here, notice how the tangent line is eventually going to become parallel to the x-axis and we won't get a tangent. So the tangent's undefined right there. Now to actually see the shape of the graph, we can go ahead and put in, do a trace on E. So let's look at point E here. And do show trace. Okay, here we go. There's that 0 we're talking about, but here we have a very steep increase as that line goes way off there. See that? So there, that's the shape of the tangent graph. Okay? Now, whereas in the tangent graph, we looked at this distance from the point of tangent to where the tangent line crosses the x-axis. We're going to see on the secant graph, we do something else. We look at the distance from the origin to the point where the tangent line crosses the x-axis. And that actually creates a secant line because we're crossing the circle twice. So let's take a look at that now, generating secants. Rolling. Oh yes, we're rolling. Sorry. When we look at secant lines, notice how the tangent line hit the circle in one point. This secant line crosses it here and over here. So that's why it's called the secant line. Now specifically we go through the very center of the circle, center of the unit circle. So now that this length here now, from the center to where the secant and tangent lines cross, that's actually going to be the secant of the angle. And we can see that it too is going to have its issues at different points. As we rotate down here, we can see that that purple segment there gets closer and closer and closer to 1. So we've actually, the secant of 1 is 0. And that makes sense because secant is 1 over cosine. Cosine of 0 is 1, so secant of 0 is 1. But now notice as we rotate upwards here, the secant starts to disappear because we need the secant line and tangent line crossing, and if they don't cross, we don't get them defined. So that's why at 90 degrees, the secant is undefined, just like the tangent's undefined. So let's wrap up then with a trace. Let's put the trace on point E. Oops. Sorry. Object properties and trace on. Oh, I have to go back to basic. Trace on. There we go. And let's see what happens as we start moving, changing the angles. Well, see, unlike the tangent, we're not going to come down to 0, we come down to 1. Right? But then, like the tangent, we have that same asymptote there at 90 degrees at pi over 2 radians. And there's the secant. Now notice if I come over here, right, it starts continuing. It's a little off there because it doesn't do the right sign. I'd have to look at the point, see that point D down there? That would start giving us the proper point for the secant in this quadrant. Okay? Great. That's possible. Okay, let's review what we came up so far with the tangent. Remember we took this distance from the point of tangency to where the tangent line crosses the x-axis. And then when it was 0, the tangent was 0, sure enough. And it's going to happen again at pi. And halfway in between is where we've got our vertical asymptotes. So let's get some vertical asymptotes in here. Look at all these. All over the place. infinite number of vertical asymptotes. Oopsie, 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 oopsie. Infinite number. And they keep going. So that gives us domain restrictions. So the tangent has got a domain of x cannot equal pi over 2, because basically the tangent of pi over 2 is undefined, plus any multiple of pi added onto that. The range is all reals. All real numbers, because look, we can take on any possible real number. And we have a period equal to pi. Not just 2 pi, but pi. Now contrast that with the secant. Remember, we looked at this length. And one thing to recall that, remember, this is going to be a right angle, because where a radius comes out to meet the tangent line at the point of tangency forms a right angle. And that creates, given our radius of 1 on the unit circle, one of our key Pythagorean identities, 1 plus tangent squared theta equals secant squared theta, because of that right triangle. Now in terms of the graph, the secant also has this issue with all sorts of vertical tangent lines, or vertical asymptotes. Look at all those. And they're occurring at the same spot as the tangent, because basically the tangent secant had that same restriction from way back at the beginning of the chapter. Let's take a little gander back at that. Remember we first defined sine and cosine and tangent, sine, all these? That's what the tangent and secant have in common. X cannot equal 0. So whenever the x-coordinate of the unit circle is equal to 0, the tangent and secant are undefined. So that would be a pi over 2 and 3 pi over 2 and so forth. Okay, back to our graph. So our domain restriction on the secant is x cannot equal pi over 2 plus n times pi. And the range is not all reals. Y's are less than or equal to -1 or greater than or equal to 1. We don't get these mid-values here because it's reciprocal. The secant is the reciprocal of the cosine. Also, as the reciprocal of the cosine, it shares the period with the cosine, and it's got a period of 2 pi, not pi. Okay. Now I want to move on to the inverse trig functions. And our role here is to find the values of the inverse trig functions. So first let's get an idea of where they come from. Okay, let's try and figure out the inverse tangent function. The problem is the tangent function flunks the vertical line test. Look at that. Oops. It flunks it over and over again with just any vertical line. So this is not invertible and still have a function. So what we're going to do is focus on just taking a small part of the tangent function that would be invertible, that would pass the vertical line test. So it's kind of natural to just take one of these branches, and let's take the branch that goes through 0. So we're just going to take this much. Let me see. Yeah, this much. That's the part of the tangent we want to keep. And let's see on the next page here. And that's what I did on the GeoGebra. And so in purple here, this is what we call the captan function. It's a subset of the tangent function that can be inverted. Its domain is restricted to just -pi over 2 is less than x is less than pi over 2. And its range then will still be all reals. We didn't lose any possible values for the tangent. Now it can be inverted, so we flip it over the line y equals x, and we get this green function. And this function is the inverse tan, also known as arctan, because you're going back to the arc that we talked about before, the arc along the unit circle. So its domain is all reals, as you can clearly see. All reals. And its range is limited between there and there. Basically, -pi over 2 is less than y is less than pi over 2. So the inverse tan only gives an angle in the first or fourth quadrants. Now keep that in mind as we take on some of our problems here. find inverse tan of 2 on your calculator. And sure enough, you get 63.4 degrees, or 1.11. To inverse tan of 2, if you want to estimate it, when do you have a slope of 2? So this is over 1 up 2, something like that. And see how it could happen in 2 spots, but the inverse tan is only supposed to give one answer because it's supposed to be a function. So it only gives this answer at 63.4 degrees. Remember, tangent being y over x is the slope of the line that goes through 0, 0. The slope of that terminal side of the angle. That's going to help us find the inverse tangent of -1 without a calculator. So that means the slope, this will produce some angle. Theta will equal the inverse tangent of -1, and the tangent of that angle theta will equal -1. So the slope of the line will equal -1. So we put a -1 slope in here. And then we say, well, which angle we're going to use, this one or this one? Well, only this one. And don't say 7 pi over 4. You've got to give the answer between negative pi over 2 and pi over 2. So that's why we only answer this as negative pi over 4 for the inverse tan of -1. Check it with the calculator. It'll agree. Also negative 45 degrees. You can see it in degrees. Okay, example 3, find. Now, before we get into example 3, let's go ahead now and explore the inverse sine and inverse cosine functions. And for that, I'm going to go to GeoGebra again. Okay, here's the work I did with inverse tangent, but now we're going to change this to sine, the sine function. As you can see, the sine function is, again, not going to be invertible. It's a function, but it flunks the horizontal line test, so it can't be inverted. So what are you going to do to invert this? Well, we have to put a restriction on it. Let's try the same restriction we tried here before, and that is from negative pi over 2 to pi over 2. Now, technically, though, we can change this a little bit and say less than or equal to. I've got to do that in a different menu. So sure enough, by going from negative pi over 2 to pi over 2, we've restricted the sign so that now it's an invertible function. Okay? And technically this should be less than or equal to because we can actually get to that point. Now, if we turn these points on, and now we can see what the inverse is going to look like. So it's a mirror image over this line. So the inverse sine, we have to do a trace. Turn this on and, do a locus of points. Locus, yes. Pick the locus point and then boom. Strange function. It also passes the vertical line test. And there's your inverse sine. Let's actually stretch this out a bit so we can see it better. There we go. Okay, here we are with trying to figure out the inverse for the sine function. And again, we can see the sine function flunks the horizontal line test. Look at that. Look at all those crossings there. That's hideous. Okay? So the inverse sine cannot be inverted as it is. So what we're going to do is, again, we're going to take a subset of the sine and go from negative pi over 2 to pi over 2. This section of the sine curve, and that can be inverted. And that's what I did here with the purple. So in purple I've got what I call the cap sine function. So if y equals the cap sine of x, It's a subset of the sine wave that can be inverted. Its domain is from negative pi over 2 is less than or equal to x is less than or equal to pi over 2. And we still get the full range of negative 1 to 1 in the y's. Its inverse, though, y equals the inverse sine of x, otherwise known as the arc sine of x, has a domain between these two values. From negative 1 is less than or equal to x is less than or equal to 1, and the range is negative pi over 2 is less than or equal to y is less than or equal to pi over 2. Now, with the cosine, similar problem. When we try and test it with the horizontal line test, it flunks the horizontal line test. Yeah. Over and over again. So we're going to take a subset of the cosine. Now, the problem is, when we start doing that same thing we've been doing all along, negative pi over 2 to pi over 2, oops, that's going to still flunk the horizontal line test. So, get out the biggest eraser, try again. This time, let's just go from 0 to pi. That will cover one complete cycle, and they'll cover all the possible values for y, and it will pass the horizontal line test. So that's what we do with the cosine. So here with the cosine, again, the cap cosine function is a subset of the cosine function with a domain of 0 to pi and a range of negative 1 to 1 for the y's. So that means the inverse cosine function, that's the one funny one up there, inverse cosine of x, also known as the arc cosine of x, will have a domain of negative 1 to 1 and a range of 0 is less than or equal to y is less than or equal to pi. Notice how we flip the roles of x and y here. And so the cosine, inverse cosine, unlike the inverse tangent, inverse sine, outputs in quadrants 1 and 2. Okay, so let's try some of these. First, try and find the inverse sine of negative 0.8 with a calculator. Did you try it? Good. You should have gotten this in radians or negative 53.13 degrees. If we look at a circle, when do we get a y coordinate of negative 0.8? So that's going to be down here or here. But we picked the one that's in quadrant 4. For the inverse sine of negative 0.8, you're only supposed to get one answer, and that's this negative 53.13 degree answer. Now let's try the inverse sine of negative 0.5 without a calculator. So you can sketch your unit circle, and when do we get a y coordinate of exactly negative a half? Well, from practicing your trig values, you should know that happens at the over 6's. That happens at 7 pi over 6 and 11 pi over 6. But neither of these are the correct answer, because the output for the inverse sine of a number has to be between negative pi over 2 and pi over 2. So I have to express this one as its coterminal angle negative pi over 6. So that's your answer. You've got to answer not just specifically in the fourth quadrant, but with an angle between negative pi over 2 and pi over 2. Negative pi over 6 or negative 30 degrees if you're in degrees. Now example 4, find the cosine of the inverse tangent of negative 2/3 with a calculator. So I think you're up for that, and you get 0.8321. Now though, let's do it without a calculator. Okay, so this gets tricky. With these types of composition problems, you might want to realize that this interior angle is an angle, this interior, the output of this function. So we're going to start by letting alpha equal the inverse tangent of negative 2/3. That means the tangent of alpha will equal negative 2/3. Now keep in mind that since alpha was the inverse tangent of a number, it's got to be between negative pi over 2 and pi over 2. That puts us in quadrants 1 or 4. and the tangent's negative in quadrants 2 or 4, tangent is less than 0 in quadrants 2 or 4. So that's how we know it's got to be a quadrant 4 angle. So we're focusing on this quadrant. So I'm going to draw that when I do the tangent of theta equals negative 2/3. I'm going to think of this as y over x, and think of it as negative 2 over 3. And so x equals 3 and y equals negative 2, as opposed to the inverse, which would put us in the second quadrant. So over 3, down 2. There we've got a point on the terminal side. And that's all you really need to figure out any of the trig functions, because the cosine of alpha will be x over r. So that would be 3 over, well, we need to figure out what r is, square root of x squared plus y squared. Square root of 9 and 4, square root of 13. So we get 3 over the square root of 13. And we're done. Because remember, we've translated the original equation into cosine of alpha, and cosine of alpha is 3 over the square root of 13, or 3 square root of 13 over 3. And you see that compares with our answer. Flange out.